Hey everyone, in this video we're gonna cover frequency divider, specifically dividing by 3 with a 50% duty cycle. So what do I mean when I say divide by 3? Let's assume our original clock is 1 nanosecond and we want to generate a clock that is 3 nanosecond time period. How can we do it? So let's examine a little bit the situation and understand what we need to make sure we're taking care of. So if we look at the 3 nanosecond time period, it means that it's high for 1.5 nanosecond and it's low for 1.5 nanosecond. So the transition is going to happen on the negative edge of the original clock. We will need to use it to solve our problem. The way to solve it is actually using a mode 3 counter. What does it mean, mode 3 counter? It means that there are only 3 solutions, 0, 1, or 2. It's a modulo 3, it's a mathematic operation. So if we look at the truth table, we can have 0, 0, 0, 1, or 1, 0, which represent 0, 1, and 2. Let's see how this thing helps us. If we look at the counter 1 column and we add it to the waveform, we get the following. When we start at 0 and we get the first clock, we stay at 0. So we started at 0, got our first positive clock, we stayed at 0. Then the next clock we transition to 1, and then the next clock we transition to 0. The next clock we transition to 0, we stayed at 0, sorry. And then we transition to 1, and so on. We're going to use this thing to help us solve this problem. The way we do it is by taking this counter 1 and shifting it by half a clock. Let's look here at the next waveform. We're going to shift it until it meets the negative edge, the transition. And by doing an OR operation between those two waves, we actually get this wave, which is the exactly clock divided by 3 we were working to achieve. I hope that was clear, and if it did, and if it was clear, I would really appreciate if you subscribe to the channel and support it more. Let's move on. How does it look in practice? So we have the mode 3 counter. We will take the count 1, we'll put it inside a D flip-flop, and this D flip-flop is shifted by half a clock, so we would want to do a negative edge. So every negative edge, we're gonna update the value, and we'll do an OR operation between the count 1 signal and the new output of this flip-flop. Now that we understand the architecture, let's look at the code. So our frequency divided by 3, we have a clock, we have a reset, and we have our output. We'll need 2 signals to help us. The Q, which is our output of the clock divider, and sorry, it's not the output of the clock divider, it's the shifted value that we're going to use, and we have our counter. Let's look at our first always flip-flop. When we have reset, we're going to reset the counter. If the counter equals 2, we're going to start to count from the beginning because it's 1, because the counter counts from 0, 1, 2, 0, 1, 2. And other cases, we're gonna increase the counter by 1. So this is our mode 3 counter. Let's look at our second flip-flop. So let's look at our flip-flop, sorry, not second flip-flop. We have the mode 3 counter and our flip-flop. Our flip-flop is operating on a negative clock edge, and it has a reset. When we have a reset, we're gonna reset the output. But if we're not in reset state, so we're gonna look at the negative clock edge, and we're gonna transfer the output of the signal of the counter 1 to this Q. And like we said, the output, the clock divided by 3, is going to be an OR operation between this counter 1 and this shifted value Q. Let's look at this in a waveform. So this is our clock, this is our reset, this is our Q shifted, this is our counter. So we can see our counter 1 is this value, and our Q is shifted by half a clock. And then if we do an OR operation between them, we actually get this clock divided by 3. I hope this video was valuable and you learned from it, and I would really appreciate if you're gonna follow the channel. Thank you.